Hello, good evening. Today I am going to explain you a problem about the heat transfer conduction with respect to convection as well. So in this, first let me read the problem. That is a metal plate of 4 mm thickness and having thermal conductivity 95.5 watts per meter square degree Kelvin is exposed to a vapor of 100 degrees centigrade on one side and cooling water on other side with 25 degrees centigrade. That means there is a plate which is about 4 mm thick. So I am going to draw the plate here. So this is the 4 mm thick plate. So this 4 mm thickness plate is having thermal conductivity K, some K is equal to 95.5 watts per meter square degree Kelvin, and there is a, on the one side of the plate is exposed to this vapor. So vapor which is at 100 degrees centigrade, and the other side of this plate is exposed to water, cool water. So that is water at 25 degrees centigrade. So in this scenario, there is a heat transfer coefficient is also given. So H of vapor is equal to given as 14,500 watts per meter square degree centigrade, and the coefficient of heat transfer coefficient on the water is H of water is equal to given as 2250 watts per meter square centigrade. So what we need to find out is the rate of heat transfer, that is Q, and overall heat transfer coefficient, that is U, and the temperature drop at each side of the heat transfer. So in order to find out that, first let us find out the Q, that is what is Q. So in order to find out the Q, there is a formula called rate of heat transfer Q is equal to U into A into the temperature difference. So whatever is the temperature difference between this layer and this layer. So let us put some points like this. So this is the point number 1 and this is point number 2. So the temperature will drop like this from 100 degrees. So this is 1, this is 2, and again within the plate the temperature will fall like this. So that is point number 3, and again after the plate is exposed to the water, so the temperature will still fall like this. So there will be 4 temperatures in the whole heat transfer. So if you see, the heat transfer rate is equal to U into area into T1 minus T4. You can write like this. So here T1 is the temperature of the vapor, T4 is the temperature of the water. So we have these two details. Area also we have. Area we can take it as per square meter. So what we don't have is U. U is the overall heat transfer coefficient. So overall heat transfer coefficient. So that is heat transfer coefficient U we have to find out. So U is equal to, there is a formula, 1 by H heat transfer coefficient on this side, convective heat transfer coefficient on this side, plus delta by K. So that is the middle part, this is the K. So this is a solid plate. So for this is the delta by K plus 1 by H of the other side, that is H of water. So if you substitute these things, 1 by the H of this is 40,500 plus delta, what is the thickness of this plate is 4 mm, that is 4 into 10 to the power of minus 3, that will be this many meters, and K, what is the K? That is the thermal conductivity. So K is given as 95.5 watts per meter square degree Kelvin plus 1 by what is the HW, that is heat transfer coefficient of water, that is 20 to 50. So if you take up these things, the U will be coming to around that is here it is 1 by U. Actually 1 by U is equal to 1 by this, all these things. So 1 by U, it will be coming to around 11.53 into 10 to the power of 5. So if you reverse this, therefore U is equal to, you will get 8673 watts per meter square degree Kelvin. So you have the value of U. So if you substitute this value here, then you will get the Q. So that implies Q is equal to U is 8673. So UA delta T. So here we take it as rate of heat flow, that is that implies Q, small q is equal to Q by capital A, which is equal to 8673 into 100 minus 25. So 100 is the vapor side temperature and 25 is the water side temperature. So therefore you will get the value of Q is equal to 650 into 10 to the power of 3, that is joules per meter square. So this is what you are going to get it, the rate of heat flow. So once you have the rate of heat flow, then you can also find the temperatures at every specific point. So because the rate of heat flow is always constant irrespective of which portion, so we can apply this formula. Rate of heat flow is equal to, here the rate of flow, so this is HA into delta T, so H into delta T. So in this portion, if you take H, what is the H? That is 14,500 into delta T means 100. We have the T1 is equal to 100, T1 is equal to 100 minus we don't know the T2, so that's what we have to find out. So from this equation we can find out T2 is equal to 650,000 divided by H, that is 14,500. So you are going to get the value of T2. Value of T2 will be coming to around 55.17 degrees centigrade. So now you have the temperature at point number 2. So from there you can calculate the temperature of point number 3, because here it is a conduction heat transfer. So therefore again we do the same thing. 650 into 1000 is equal to K, the thermal conductivity, into delta T. So here the delta T is equal to T2 minus T3. So T2 minus T3. So we already have T2, we have found out. So that is K is equal to 95.5 into T2 is equal to 55.17 minus T3, we don't know. So that's what it will give. T3, you will get T3 from these two equations by equating this. So that is 650 into 1000 divided by 95.5, then you will get the minus 55 point, this will come here, so that is 55.17. If you do this one, so you will get the value of T3 is equal to, so T3 is coming to around 53 degrees, so which is 53 degrees centigrade. So that means temperature at this point is 53 degrees, and T4 we already know, that is 25 degrees. So T4 is 25 degrees. So we already have. So now we have all the temperatures, that is T1, T2, T3 and T4. So this way we can solve the problem of heat transfer within the conductivity plate and surrounded by convection atmosphere, like one side vapor and one side water. So if a solid conductive material is surrounded by the convective substances, then it's a problem of conduction plus convection. So using these relations we can find out the overall heat transfer coefficient and the rate of heat transfer, as well as the temperature in between the points. So the internal temperatures also we can find out. So the temperature gradient will be like this. So hope this will help you to solve the heat transfer problems. Thank you.